Welcome back for the second video on this chapter 6 discussion. We're going to finish up the topic of heat and energy and apply it to biological systems, which is what you and I care about. And we're going to then talk a little about reactions that don't do what we think of as chemistry. We think of chemistry as being reactants, reaction occurs, products, but that's not always true. And so we have to talk about those reactions that can go forward, meaning they can take the X and Y and make Z, or they can take Z and fall apart to X and Y. And they might do them at the same time, dynamically, all the time. So we'll talk about that after we finish up heat. And really, all I want to finish up the discussion of heat is saying that when you talk about reactions, you talk about biology, we're really talking about combustion in your stomach and why you do it. And you do it for energy. So, how does that energy realize itself and how do you use it? Now, obviously, when you eat a bowl of frosted flakes, you give off all this energy. And so, when bonds are broken, when large molecules, and I don't just mean the frosted flake itself, but the proteins and the carbohydrates and the DNA, I know that sounds weird, but the DNA in the frosted flakes are all digested. They're all torn apart by acid and proteins in your stomach. By the way, when you have an enzyme in your stomach, an enzyme is a biological catalyst. They do chemistry. All proteins are not enzymes, but all enzymes are proteins. They're a type of protein that does chemistry. Anyway, here we have some frosted flakes, and it breaks down into small molecules. Now, that act of bond breaking gives off energy. And that's good because that's why we ate a bowl of frosted flakes, for the energy stored in that sugar and protein and carbohydrates and fats. But it doesn't make sense that that energy that you're gaining from the frosted flakes can be turned into heat. It will initially. But what do you do with that heat? You can't send a packet of heat to your toes or your brain. So what do you do? What you do is you make a molecule. You make a small molecule. And when you make that molecule, you're bond making. Now remember, breaking apart frosted flakes, giving off energy. Bond breaking is exothermic. It gives off heat. Bond making is endothermic. So what you do is you turn that frosted flakes, chemical stored energy, into a new form of stored energy that can go through your bloodstream to your brain and your toes. And we'll talk about this molecule for the rest of this course, but you've probably heard of it. It's called ATP. It's basically the gasoline of your body. It's the stored energy you're going to use to work your brain and your lungs and your heart and your toes. So you create this molecule ATP. You sort of store the energy in the TP part, the triphosphate. Remember, 8 means oxygen, so it's phosphoruses with oxygens, and you have 3 of them on this A molecule. So A triphosphate. And you can carry that all through the body. And then let's say you're going to make a red blood cell. When you make a red blood cell, you need all the proteins inside the red blood cell, billions of proteins in every cell. You need the DNA at the core of it. You have to make some DNA and in the nucleus. All that bond making requires energy. You can imagine with all those proteins being made, you need a lot of energy. So ATP arrives, and it says, well, I've got all these bonds I can break. A triphosphate can break those phosphate bonds, and by doing that, breaking bonds gives energy, and you can make small molecules into big molecules. You can make cells. You can reproduce old cells. You can make new types of cells. You can grow. You can do all kinds of things. And I kind of do want you to know that that process of eating Frosted Flakes, of taking large molecules in the stomach and breaking them down and getting the heat out, is catabolism. And that process of taking the small molecules of a new cell and making the useful proteins and DNAs of a cell is anabolism. You should know those words: catabolism, anabolism. Those are good words to know, by which I mean you need to know them. And you should know that bond, and it's intuitive, bond breaking, eating an apple and digesting it, is going to give off heat. ATP is the energy carrier around through your body, and that the process of making bonds, making new elegant you, is going to require heat. Bond making requires heat. And that's sort of the chapter 6 heat and energy topics I want to talk about, with the exception of, remember I said that we're not really talking about how long a reaction takes. Just because you know that a reaction is exothermic doesn't mean that it takes a second. It might, like propane, but it might be an apple that you digest over hours or weeks, or some chemistry that's exothermic but takes years. So it's not temporal. We should talk at least briefly about how you would speed up a reaction. So how would you speed up a reaction? How would you speed up any reaction? Well, there's a certain logic to how you'd speed up a reaction. There's an old chemistry adage that a slow reaction is God's way of saying, heat that sucker, right? So one way to speed up a reaction is to add heat. And that is intuitive. Whether it's endothermic or exothermic, if you put that activation energy in, more molecules will have enough energy to collide at the right orientation and make a product. And the more collisions with the more energy, the more product you make. How else might you have more reactions with enough energy to react, make a product? We'll increase the concentration. So if you have a big beaker of water with a couple of molecules in it, and they never see each other, and when they do, they might have enough energy, and they might not, that's going to be slow. If you pour in more so that they're always bumping into each other, the chance that two will hit with the right orientation with enough energy goes up. So for a liquid or a gas, these molecules that move, not possibly like this, but move, those molecules, for gases or liquids, you can increase the concentration. And that's kind of intuitive as well. If you think about it, how do you make a reaction go faster? Have lots of collisions with more energy. So heat it or higher concentration. For solids, you can't really do that. You can't really increase the concentration. It's a lump of magnesium metal you're trying to set on fire. And it doesn't burn very well. So how would you make it burn faster? Well, you want more reactions more rapidly. And it's sort of akin to, how do you get a big block of ice to melt? You want more collisions, but the ice can't move. So how do you get it to melt faster? You smash it into small pieces, because the more surface area that has a chance to react, the better chance of reaction will occur. So similar with magnesium, If you had a block of magnesium, you could, you know, really with a Bunsen burner, you couldn't get it to light. Grind it down to particles and put it on a stick, and you have a sparkler, right? Which will burn brightly and beautifully and fun with just a match. So with a solid, the more surface area where reactions can take place, the faster the reaction. So we're talking about here about kinetics. And all of these ideas you see at the bottom there, concentration, temperature, surface area for a solid, those all increase a reaction. And what they are all doing is providing a method by which more bicyclists who are at the bottom of that hill trying to get to that village can get over the hill. How do you get the bicyclists over the hill? Give them more energy, right? Give them all some, you know, some kind of energy source of fuel, of food. That's heat. Or have more bicyclists, because if you have lots of bicyclists, there's a chance some of them have enough energy to get over the hill. If you have one or two, maybe neither of them are strong enough to get over the hill. Now, all of this is true. And there's another way to increase a reaction. And that way of increasing a reaction rate, because kinetics is about reaction rate. How fast? How can you speed up a reaction? Well, logically, make the hill smaller, lower the activation energy. You don't change the reactants and you don't change the product. The bicyclist still goes to the village. It's just that huge hill, that activation energy has been diminished. And so the bicyclist can go through a tunnel. See that red dotted line? That red dotted line is that you add some external material. And that external material, from in one way or another, causes a slow reaction to go faster. And those external materials that can provide you with that are called catalysts. A catalyst is an amazing thing. It makes a slow reaction go faster. And we have already mentioned that enzymes are how your body make biological systems possible. Enzymes take reactions that wouldn't necessarily occur and make them occur. Your DNA is full of the codes for enzymes that you need to do things like fight off infection or, you know, digest food. And if a protein does chemistry, if it's a biological catalyst, if it does chemistry for you, a catalyst is a enzyme is a biological catalyst. And with that bombshell, we are going to stop talking about heat and energy, and we're going to talk about something totally different. What we're going to talk about is the idea of equilibrium. And we have a sense of it. We have a sense that some things don't go in one direction and that's it. They go forward and back, right? So if I had a pan of water, and I had in this pan of water, there are molecules, and I know intuitively that all the time water is evaporating. There are some molecules in that pan of water that have more energy than other ones, and they're evaporating. But in this room right now, there is water molecules in this basement, too many water molecules. But there are water molecules, and they're dropping down and they're falling into this pan. And so all the time, the water is evaporating because some molecules have extra energy and some are condensing and they're going back. And if the pan doesn't change the amount of water you save, you come back tomorrow and the water level is the same, then you would say that those two processes are in equilibrium. And the way we indicate that is with double arrows, right? So I could say liquid water, and you can't see that. So water is a liquid and water is a gas are in equilibrium, meaning water is evaporating, water is condensing. I can disturb it. I can have a very dry basement. And if I have a dry basement, the water in the liquid form, see no water in the gas form, and it'll evaporate. Maybe our pan and you come back and that pan water is actually going up in level because the amount of gas water is so high that it's constantly going into the pan, but the amount of water in the liquid form can't get in. Water in the gas form. This idea is equilibrium. So we're going to talk about that briefly, and we're going to talk about it as a biological issue. And it is a biological issue. It's a serious biology problem or issue. So there is my water reaction. Let's say I have, lots of water in the air. I can get more water into the gas liquid phase because it's all condensing. Let's say the basement is very dry, water will evaporate into it. But if I had the right humidity, I would have water going into the liquid phase, back into the gas phase at the same rate. And if that's true, we call it equilibrium. And you always make these silly little half arrows because that's how we indicate equilibrium. I'm showing you what's known as the Haber process, discovered by Fritz Haber, and it's a long story I'd love to tell. Fritz Haber figured out how to get nitrogen out of the air. Nitrogen is 80%, roughly speaking, of the air, and yet we can't use it. We can't turn it into anything. We need soil bacteria to fix the nitrogen out of the air so that we can use it, because our body's full of nitrogen, but we can't ingest it by breathing. 4 out of the 5 particles you breathe are useless to you. Only 1 out of 5 are oxygen, 20%. So Haber figured out, to the detriment of millions of men during the First World War, how to fix nitrogen, how to get it out of the air. And what he realized was that this famous balanced equation, nitrogen plus hydrogen makes ammonia, NH3 is ammonia, is in equilibrium. And so how would you make ammonia? Well, you put nitrogen and hydrogen together. Well, how do you make it faster? You would heat it to get it going. You would have high concentrations. You would add a catalyst. Remember all those things that made a reaction faster? And you would eventually get to an equilibrium. See that nitrogen and hydrogen are in equilibrium with ammonia? Okay, now you've reached equilibrium. And your problem is you want ammonia. You don't want nitrogen and hydrogen. But at some point, when you reach equilibrium by heating it up and adding lots of nitrogen and hydrogen, you make ammonia, and now the ammonia is going back and going forward and going back, and it's in equilibrium. And by the way, throwing off heat. In this forward reaction heats a product, right? So the question is, how could you shift this equilibrium? I want to make, I don't want nitrogen and hydrogen. I want ammonia. I want NH3. Yet my NH3 is constantly going back and making nitrogen and hydrogen. It literally falls apart. I don't want it to. Well, Haber relied on a Frenchman whose name was Le Chatelier. And what Le Chatelier said was, if you have an equilibrium, like the Haber process, all you have to do is stress the equilibrium, put it under pressure, and it will shift to relieve that pressure. It will try to restore that equilibrium. In other words, it's like a balance beam, a seesaw, a teeter-totter, and it's balanced. There's the same reaction we saw on the last slide, and it's all balanced. Nitrogen and hydrogen smash into each other and make ammonia. Ammonia falls apart and goes back. Le Chatelier said to Haber, indirectly, well, if you could stress this system, you could get more product. So how can I stress this system? So here's what Haber said. Let's take a hypothetical reaction. Here's a hypothetical. It's an endothermic reaction. Heats a starting material, heat, and then X plus Y makes that. But Z will fall apart to X and Y, giving off. If you stress the reaction, if you change the amount of anything, you'll have an effect because the equilibrium will always try to maintain. Let's say I add a lot of X, so X goes way up. Right? I add a lot of X. Now, there's lots of X. Bouncing around this balloon hypothetically, and it smashes into all the Y's. Well, X plus Y makes Z. So all of a sudden you're smashing into all the Y's a lot more commonly. So the Y's get used up and the Z's start getting made. In other words, add something on this side and you'll drive the reaction that way, away from where you added something. Right? And it's logical. You add X, it'll use up Y and make more Z. So you drove it that way. That's what Haber was trying to take advantage of. And in fact, what Le Chatelier said was that, well, be aware, heat part of this reaction. If heat plus X and Y makes Z, if I add heat, right? If I add heat, well, heat plus X and Y makes Z. So if I add heat, even heat. But here's the other thing. If you could somehow take something out, let's say you could take out heat, or you could take out X. Notice that whether I'm talking about X or Y or heat, they're all materials, right? Let's say I could take out heat. Because Z is supposed to be making X and Y, and then X and Y are making Z. But X is leaving. And Z's like, oh no, I'm supposed to be making X and Y, there's no X. So what will happen? Z will say, I got to fall apart and make more X and Y. So if I take out X, remember, if I take it, X, I drive it to make more Z. If I take out X, the Z is like, I got to fall apart to X and Y in heat. That will go down as it makes more X and Y. It's going to try to compensate everything tries to compensate. Le Chatelier said, if you stress the system, it will try to compensate. Right? So what did Fritz Haber realize? Well, he realized how to get to equilibrium. And then he said, look, if I add more nitrogen, if I increase nitrogen, if I have more on this side, it'll smash into all the hydrogens and make ammonia. If I take the ammonia out as I'm doing it, if I could condense the ammonia, the nitrogen and hydrogen be like, wait, the balance beam's not balanced. We should make more ammonia because the ammonia is disappearing, right? If I could take heat away, well, heat is a product here. If I take heat away, well, these two are like, where's our heat? We were supposed to make heat, and they'll combine to make more heat. Anything you take away, it shifts towards that to make more of it. So we realized get it up to equilibrium and then have a reaction where the heat's being pulled out, the ammonia is being pulled out. You keep adding nitrogen and hydrogen, and you can make a lot of ammonia. So this is called equilibrium, and Le Chatelier talked about it. And we always find reactions that are under stress. So what's the most famous equilibrium on Earth? The most famous equilibrium on Earth is water. Water itself is always falling apart and making a little bit of H and OH. And that's a very famous equilibrium that we'll talk about in chapter 9. What's always true is that water is falling apart to H plus and OH. Now, that's not one direction. All the water on Earth could eventually fall apart, right? What's also true is that H and OH, a proton and hydroxide, are making water. So, and you can stress this system. If you add a lot of H, we'll use up the OH and make more water, right? You'll drive the reaction away from the thing you added. That's what Le Chatelier said would happen. So, that said, a lot of what we're going to talk about in terms of equilibrium is about acids and bases. Ammonia is famously a base. You add ammonia to water, it makes this ammonium and hydroxide. If you add lots of ammonia, that'll use up the water and make more ammonium and more hydroxide, which is actually the base, right? So base and acid, this is a good word. The conjugate acid of this base is the version with the H plus. We're going to talk about acids and bases. And the conjugate base of this acid is the version without the H plus. And these are in equilibrium. And I want you to have that sense of equilibrium. Why do I care? Because we'll talk about this again. Human blood contains carbonic acid. Carbonic acid comes from carbon dioxide. And I know you think, well, you need to breathe out all that carbon dioxide that's the product of combustion, but you actually use some of that carbon dioxide because you can make carbonic acid. And you need that in your blood because it acts as a buffer. And a buffer is something that resists pH change. Again, we'll talk about this in chapter 9 in more depth. But there's an equilibrium here between carbon dioxide and water and this carbonic acid, which you need. So if you take carbon dioxide out of you too much, let's say you're breathing deeply, which is called hyperventilating, you can lose carbon dioxide. And Le Chatelier says if carbon dioxide goes down, carbonic acid makes more carbon dioxide to relieve that stress. If you're breathing shallow, let's say you have been in a serious accident, you're not breathing deeply, you'll have carbon dioxide go up and shift to more acid, carbonic acid. You don't want too much acid. Obviously, you don't want your blood to become acidic. So anyway, that's the idea of equilibrium. Now, I will say it was kind of a whistle-stop tour of equilibrium. You need to do that homework and read the text and give the PowerPoint some thought and realize that we'll talk about it in some depth in chapter 9 because all of acid and base chemistry is about equilibrium. So it really matters. So anyway, quiz coming up, and watch for my newsletters that I'm sending all the time. Please read them. Although if you made it to the end of the second video, you're probably the type that actually reads my emails. So preaching to the converted. Anyway, any questions, any concerns, please feel encouraged to contact me here. And I'm hoping these videos that I've been making have been of value. Thanks for your time.